I'd now like to welcome Dr. Carolyn Tiddy. Carolyn is a Senior Research Fellow at the Future Industries Institute of the University of South Australia and has a significant role as Coordinator of the Education and Training Program within MinEx CRC. Carolyn will speak today on some of the new research she's been undertaking, Synthesis the Tectonic Evolution of Proterozoic Australia, with a focus on the setting for IOCG mineral systems of Southern Australia. Carolyn, welcome to the stage.
Thanks very much, Rowan. And I'd also like to thank the Geological Survey for inviting me to present today, and also for allowing or for having a MinEx CRC booth, which is on the wall on the other side here, where you can actually come and see some really cool virtual reality models we have of our new drill rig. But I'm not going to talk about any of that today. What I am going to do is present some work that I've been working on with Dave Giles for quite a few years. And again, have to thank the survey actually for allowing me to be part of their writing days that they've had over the last few years, which have allowed me to really progress this, and especially with discussions with people like Anthony Reid, Mark Pauly and Claire Wade. So thank you for that, I very much appreciate it. So what I want to present today is an alternative model that Dave and I have put together for the period of the evolution of Australia from 1600 to 1570 million years ago. There's been a lot of models that have been put forward at this time. Recently there's been the model by Pete Betts that was plume modified orogenesis that Dave and I were co-authors on. And there's also been the model by Roger Skiro that was published last year that proposed foundering of a pre-metasomatized subcontinental lithospheric mantle. These models are really interesting and they account for many aspects of geological features within this time slice, but they do have some limitations. So what we've tried to do is put together a holistic model that accounts for the complexities of this event, and that's also self-contained, so doesn't call on any external factors that would actually account for some of the geological features. So concentrating on South Australia, the features that we see that are 1600 to 1570 age, we see a lot of deformation. In areas such as the Curnamona province, where we see intense shortening, and we also see exhumation in the Mount Woods Inlier, for instance. We see a lot of high temperature metamorphism through the western, northern, northeastern and southern Gawler Craton, as well as over in the Curnamona province. There's a lot of mineralisation through the Olympic domain, so we see our IOCG mineralisation, and then we also see copper, gold and base metal mineralisation through the central Gawler. And we also see an interesting magmatic history in terms of the emplacement of the Hiltibus suites shown here in red, and also the Gawler Range volcanics. And the Hiltibus suite is quite interesting. This is a cladogram of published ages of the Hiltibus suite, and the granites shown on there by these little blobs are coloured according to the chemistry that was determined by Anthony Budd in his recent PhD thesis. And what we see is that older granites are concentrated in the northern Olympic domain and tend to be dominantly A-type. And then as we move to the southwestern Gawler Craton, we tend to get younger granites that are dominantly I-type. And I'll come back to the importance of this later in the talk. So the kind of model that we wanted to actually develop is one that would be consistent with tectonic settings before and after the 1600 time slice. We wanted to be able to account for switches in tectonic regimes from compression to transient extension. We wanted to be able to account for the high temperature and low pressure metamorphism that we see. We wanted to account for the development of the Hiltibus suite, its variable distribution and its variable chemistry. We want to be able to account for schlum metasomatism because that's very important in mineral genesis. And in terms of mineral genesis, we want to understand its distribution, links with magmatism and its chemistry. So the model that we've developed, it starts at 1670, so just after the Kimberley orogeny. Due to the limited time, this is an abbreviated version of this model. So please do excuse the outlandish statements that I may make. So the model starts with the system being in a state of rollback. So what we have at this time is we have asthenospheric upwelling and development of back arc basins over inboard of the plate margin. These extensional basins were basins into which major sedimentary sequences were deposited, such as the Williama supergroup of the Curnamona. Whether or not we put the Tunkilia suite into the subduction environment, that's debatable. Doesn't matter, but by 1650, we know that we were definitely in subduction because we have the St. Peter suite come in, those alkaline arc signature magmas. We have continued extension and development of basins over in the back arc area. In those areas, we see elevation of geothermal gradients significantly above average geothermal gradients. We also see lithospheric thinning and thermal weakening of the lithosphere. That first part of the model is very similar to what Pete has actually put in. So we've drawn on those aspects of that model, as well as other aspects of Rogers that I forgot to mention before. 1604, we see a change. So at about 1604, we have the arrival of a continental plateau that's then subducted. An oceanic plateau. Subduction of that oceanic plateau changed the system from one of rollback to one of flat subduction. We see that the St. Peter suite magmatism is shut down, and we start to see basin inversion over in these previously back arc extensional areas. That basin inversion is associated with high temperature, low pressure metamorphism, and that's because those elevated geothermal gradients associated with back arc extension are inherited into orogenesis. This is the point where the fluorine story becomes interesting. So we know that a lot of the IOCG deposits in the Gawler are very fluorine rich. Claire Wade did a really interesting study recently where she looked at the mafic components of the Hilltopper suite, and she showed that the sclum underneath the Gawler is heterogeneously enriched. She used the thorium-niobium ratios of the mafic components of the Hilltopper suite as a proxy for sclum enrichment, where higher ratios are associated with higher degrees of sclum enrichment. When we plot Claire's data of thorium-niobium against fluorine, we see a positive correlation. So that's indicating that fluorine enrichment is associated with sclum enrichment. So if we've got that, then where does that fluorine sit? We then had a look at a paper by Kohler and his colleagues who were looking at the Garda province over in Greenland, and they showed they used a potassium versus fluorine plot to show that a lot of the mafic rocks are associated with phlogopite, and the fluorine's associated with phlogopite. So we plotted Claire's data on that diagram, and we actually see that quite a few samples plot within the phlogopite field. So we're postulating that the fluorine is associated with phlogopite, which is a mineral that's commonly seen in enriched sclum materials. So if we have fluorine enrichment, how do we get fluorine enrichment? One thing about fluorine is that it will not be released during slab dehydration. When you dehydrate a slab, you'll get fluids that are hydrous, that are sulfur-rich, and that are chlorine-rich, but that are fluorine-poor, and the fluorine will actually be taken deeper into the system. It will be released when we have melting of the downgoing slab. So if we have, how do we actually get melting of our downgoing slab within a flat subduction environment? That can happen if that flat slab is exposed to hot asthenosphere for a prolonged period. You can get melting. And also, if you switch from a flat subduction environment to a rollback environment, you're exposing the downgoing slab to hotter asthenosphere, and you can get melting. So we're suggesting that we start to get slab melting at this point in our flat subduction environment, and that's going to actually start to produce our older A-type Hilltopper suite granites. Let's move on to 1595, and this is where things are really starting to move on. We're getting some quite serious basin inversion, shortening going on over in the Curnamona province, for instance. And what's happening here is we're starting to see some differential stresses between our buoyant posterior oceanic slab and our dense frontal slab is causing stresses that are going to be concentrated at the tip of that oceanic slab. And that's going to start to cause slab tearing. We're going to get upwelling asthenosphere, partial melting in the sclum, and development of our A-type magmatism and our felsic flare-up. The upwelling asthenosphere is going to allow for uplift and transient extension, especially within the Olympic Dam area and IOCG mineralisation. So if we hone in on the Olympic Dam area, what we can see here, this is just to explain in a bit more detail all of that quite complex time. We have the introduction of our anhydrous slab melts and heat from our asthenospheric upwelling. It's causing melting of our sclum and development of mafic melts. These mafic melts then pond within our lower crustal mash zone, and they will then undergo assimilation fractionation processes and or partial melting to produce progressively more silicious magmas that move up into upper crustal or mid-crustal levels. These evolving silicious magmas are evolving and fractionating, and the fluids that are exhaled from those will be very volatile rich, fluorine, chlorine rich, can carry metals, and when stalled will produce our IOCG mineralisation. And then when these magmas reach the surface, that's when we get our lower GRV, and then also at 1587 we get our upper GRV felsic flare-up. So it's a very complex time, and that's a very brief explanation of that. At 1585, things start to change a little bit. So we had our dense frontal oceanic slab is starting to actually pull that buoyant posterior slab down a bit. So we're getting a bit of slab retreat and a return to normal subduction type environment. We have an asthenospheric wedge starting to develop, and we have an upwelling asthenosphere. Within that more normal subduction environment, we're getting slab dehydration to produce sulfur-rich hydrous fluids that then interact with our sclum, and eventually we get our copper-gold base metal sulfide-rich mineralisation in the central Gawler area over here. We see I-type magmatism that is more typical of a subduction zone, and we see magma migration. Magmatism migration, and that magmatism migration is what we can see on this cladogram here, where we move from older granites over in the Olympic domain down into the southwestern Gawler Craton, where we have our generally younger granites. The analogue that we've drawn on for this is the laramide orogeny over in the western US, where we have the Farallon slab that was retreating, and magma migration was moving trenchward at about 50 million years ago. So it's a modern analogue of what's going on here. The magma migration introduces or highlights the issue that this is a 3D problem. I'm showing you two-dimensional images, but this is a 3D problem. This is an interesting study that was published by Hu and Liu in 2016, where they looked at the Nazca plate. So what this shows over here is the top, on the right-hand side of the trench, is the top surface of the Nazca plate. What they did is they actually noticed that where we see these aseismic ridges, such as the Nazca Ridge or the Juan Fernandez Ridge, they actually modelled slab tears starting to develop within the Nazca plate. Those are areas where the asthenosphere can actually well up and intrude, and come through and actually start to cause magmatism, and in some cases volcanoes. The actual geometry of these downgoing slabs is really complex. There's another study by Gidon Rosenbaum that was just published that shows in this same area in the Andes that these slabs are really complex shapes. So not only are we going to be getting upwelling asthenosphere from this way, but it's also going to be coming in from the sides to actually promote all of that magmatism. Another thing I touched on was that we have a change in mineralisation, and this is where we again looked at the Andes. And we looked at there's a study by Richards and his co-authors in 2017, and what they did was they looked at the development of porphyry copper gold systems versus IOCG systems at roughly the same time and in the same tectonic setting. And the thing that they said is really critical as to whether or not you'll get the copper gold mineralisation or the IOCG mineralisation is simply whether or not you have a sulphur poor or a sulphur rich system. So we drew on that to actually inform our model, but the difference that we said is that within the Gawler, the IOCG mineralisation is also fluorine rich. So instead of being within a back arc environment, we're saying that the sulphur poor magmatic system was sourced by the sclum that was modified by the slab melts. This is the last stage that we have of our model. I think that's probably enough by now. So at 1575, we've said that magmatism was shut off due to rebound of that slab. So we have decoupling between the downgoing buoyant oceanic plateau and the frontal dense slab. So magmatism is shut off, so it's the Hilltobin magmatism. We see the subduction continues to the west of the Gawler Craton, as evidenced by the 1530 potentially arc-type magmas in the Kumpana. And then we have continued plate margin activity up in the northeastern parts of Australia, such as around Mount Isa and phase 2 of the Isa orogeny, and also around Georgetown. So, in conclusion, we're putting forward an alternative geodynamic model that's putting the Proterozoic Australia within a supra-subduction zone environment. We're using modern-day analogues as well as previous studies to actually inform this alternative model. We're trying to account for the complexity, as many of these preserve complex features within that 1600 to 1570 event, within a self-contained model that doesn't call on any sort of external factors. And with respect to the generation of IOCG versus our porphyry epithermal copper-gold type deposits, it's not actually the type of magmatism that was important, it's whether the system is sulphur-poor or sulphur-rich, which in turn is dictated by whether we have slab melting or slab fluids that actually interacted with our sclum. Thank you very much.